Nexus Aurora, IAC 2023, Baku.
My name is Elliott, Orion, Ruzicka, and I'm a registered architect operating out of Manhattan, New York. I've been working as an architect for the last 7 years or so, but most of my space design related stuff is on my website at orbital.design. I'm also affiliated with the community space design community Nexus Aurora. And with that, shape matters. If there's anyone here that doesn't agree that this applies to space habitat design, it's my hope that by the end of this presentation, they will think differently. It's also my hope that the results I will be presenting at the end will surprise and possibly even shock you. Now, the concept of polyhedral space habitat modules has been explored in prior research by Frisina, Devek, Howie, and Ekbla. And while these studies present numerous arguments supporting certain candidate polyhedra based on desirable qualities, little in the way of rigorous evaluation has been dedicated to determining the most ideal polyhedron among these candidates by way of employing many consequential evaluation metrics. Now, the aim of this study was to determine as close to objectively as possible which polyhedral form is the most suitable to the application of space habitat modules. Although this study is not absolutely exhaustive, it stands as the most comprehensive evaluation of its kind at the time of publication. And furthermore, it presents a novel conclusion, one that has not been explored by prior researchers. And this is an important question to answer sooner rather than later, as work to create polyhedral space habitat modules that are constructed in orbit is currently ongoing by the Aurora Institute. So due to first mover advantage, the first shape used is likely to set a standard early on, and any disadvantages will be perpetuated. Now, the aim of this study was not to defend the specifics of polyhedral space habitat module construction. So any questions about specific mechanisms or applied technologies that would be common to any polyhedral form are beyond the scope of this study. Now, in this presentation, I'll cover which candidate polyhedra were selected, which metrics were used to evaluate the candidate polyhedra, and what analysis methodology was used to process the raw metric value, and finally I'll be presenting the results. So, this is an abbreviated version of the candidate polyhedra selection criteria, and I'd be happy to discuss this in greater detail at a later time. But shortly, the candidates were selected from the simpler side of the spectrum first. So the shorthand for this is just how complex does it look, how many faces does it have. They should be specifically convex. They should be, their faces should be orthogonal to the radial line going through the center of the faces. Special consideration was given to advantageous qualities like space filling, and also shapes that were that are currently being explored by other researchers. And because I can't study them all, the selection was limited. In this case, I studied 10 polyhedra. So, firstly, the first selection was the tetrahedron composed of 4 regular triangles. On the right hand for each of these, you'll see what it might look like for each of these to be connected on their faces to each other in an agglomeration. Next was the octahedron. Next was the cube, composed of 6 squares. The octahedron, composed of 8 regular triangles. The dodecahedron, composed of 12 regular pentagons. And these are the platonic solids. The icosahedron, composed of 20 regular triangles. The rhombic dodecahedron, composed of 12 rhombi. the triangular prism, composed of 2 regular triangles and 3 rectangles, and the hexagonal prism, so these are space-filling shapes, as I mentioned, composed of 2 regular hexagons and 6 rectangles. It's worth noting here that these prisms, the proportions of them were selected to be the proportions that maximize volume to surface area ratio. Next is the truncated octahedron, composed of 8 regular hexagons and 6 squares. And finally, the truncated icosahedron, composed of 20 regular hexagons and 12 regular pentagons. This is the shape that is being preferred by the Aurora Institute currently. So I've spoken about the selection of candidate polyhedra, and now I'll explain the evaluation metrics that I used. 14 were selected in total, and I'll go through each of them now. So first is the number of faces. Fewer faces means less complication in assembly and operation, as well as fewer redundant systems. This is for polyhedral modules that would be constructed in orbit after being packed flat in a fairing. Number of face types. So fewer face types, ideally a single face type, means less engineering, fabrication, and qualification testing costs, as well as a simpler deployment. Number of edges. Fewer edges simplifies the exchange of utilities between panels, as well as reduces the number of gaskets to vacuum. That's easy. Volume to surface area ratio. The greater the ratio, the more volume can be utilized per mass unit. It's also more mass efficient. Deployed volume is larger than the stowage volume. This is pretty important when you want to assemble things. You want to make sure that the final assembled volume is actually larger than the volume that was used to contain it in the fairing. And not all of the polyhedra candidates met this criteria. You see 2 examples, one that isn't larger than the fairing size and one that is. Next is the face apothem similarity. I'll try to explain this one. The module face panels will have many integrated systems. And for polyhedra with more than one face type, it's advantageous for the sizes of the panels to be as similar as possible, so as to efficiently utilize the area and volume of the panels with similar systems. The face apothem is a convenient shorthand for the face size in this respect. Face tension. An internally pressurized surface will resolve the outward forces through face tension, just like a balloon. A lower face tension is advantageous because, again, it means a greater mass efficiency due to the structure. Joint stress. Joints are weak points in polyhedral structures, but sustain the most stress in pinned face connections, as the stress is a vector product of the pressure reaction, here shown in red, and the face tension shown in blue. For the same reasons previously mentioned, lower joint stresses is advantageous. Simulated stress. You can't just rely on calculations. Each polyhedron was modeled in Fusion 360 as hollow solids, and they were internally pressurized, and the max stress was recorded. Again, the lower the stress, the better. Space filling. I consider this to be one of the most important metrics. Space filling shapes allow for the following benefits. The complete utilization of 3-dimensional space, the reduction of exposure to radiation on interior modules, the more connection possibilities and flexibility, looping pathways instead of dead-end corridors, which is important for circulation around the modules, structural rigidity, and also the ability to contiguously enclose a volume of space. So you can enclose a volume of space using just the modules, so it's kind of like getting free protected area, free protected volume. Next is the number of face connected modules. It's advantageous, this isn't a good example, by the way, that's a counterexample. It's advantageous to have a greater number of modules that can be connected to any given module. And this increases the efficiency of both circulation operations. In this case, this is the icosahedron, and I think the average number of connections you can make is between 2 to 3. So you can't connect to more than 2 or 3 modules. Lattice forming. Similar to space filling, a lattice allows for looping pathways, better wayfinding, and structural rigidity. Unfolding deployability. Now, this is the ability for flat-packed panels to unfold along their edges until they're fully deployed, as opposed to, I think, what the Aurelia Institute is seeking, which is pseudo-stochastic assemblability. This capability maintains the connection of the panels during the assembly and eliminates the necessity for guided systems to be integrated into each panel. And finally, fit in a rocket fairing. We can't necessarily rely on large launch systems that are not currently operational. It's important that large modules are able to fit inside currently operational launch vehicles. And for this particular metric, a notional final module volume was assumed. So I've gone over the selection of the candidate polyhedra and the evaluation metrics, and now I'll explain the analysis methodology. The goal of the analysis is to take the raw values from the evaluation metric methodologies, the number of faces, for example, and arrive at a best performer. However, there are 3 obstacles in the way. The raw values, or performance disconnect. So the raw values don't necessarily represent the performance of a given candidate compared to the others. There's dissimilar units. The units between the evaluation metrics can be completely different, and even of different magnitudes, which would be like comparing grapes to watermelons. And finally, the weighting. Not all evaluation metrics are as important as every other one, and some weighting will likely need to take place. This graphic shows how the raw values were processed for each metric using a single metric as an example. In figure A, we see the raw values for each of the candidates side by side. We find the poorest performer, and we use that as the baseline. Now, the differences between that baseline and the raw values represent the performance values, shown in figure B. This solves the performance disconnect that we just talked about. We can then add up all the performance values and sum them, and that is shown in figure C here. We divide each performance value by the sum of the performance values, which results in a normalized performance value that can be seen in figure D, where the sum of all the normalized performance values is 1. And this solves the issue of dissimilar units. This leaves the weighting, but we'll get to that in a moment. Using these more normalized performance values, we can create a weighted analysis tool where we can input the normalized performance values here for each evaluation metric. We can add weights to them. In this case, they're all just weighted at 1. And it will output a final score shown here. But what weight should we use? Without knowing how every weight would turn out, it's impossible to objectively determine how each candidate polyhedra stacks up against each other in the individual minds of everybody. That might be asking the question. So I wrote a Python script that tests all the combinations of importance levels up to 5 levels of importance, up to 5 integer weights. And this took nearly 6 days to run. Some of you might ask, why not 6 levels of importance? And to that, I say an analysis of 6 levels would be 6 to the 14th power, which would have taken 70 days for my computer to run. So forgive me. I was expecting a descending distribution for the results, whereas I can analyze under which circumstances different polyhedra would perform best, but that's not at all what came out of this analysis. This table shows the candidate polyhedra along with their average ranking, the number of times the polyhedra were ranked first, and the percent of the total combinations where the polyhedra were ranked first. If it's not immediately obvious, I'll call your attention to this figure here. In every single one of the 6.1 billion combinations of importance factor weights, the rhombic dodecahedron was ranked first. This means that no matter which weights one puts on each of the evaluation metrics, at least to an importance level of 5, the rhombic dodecahedron will remain on top. The truncated icosahedron, by contrast, with the largest volume to surface area ratio, is ranked 6th. I conclude that the rhombic dodecahedron should be considered the default for any prospective polyhedral space habitat module design. And furthermore, I propose that the truncated icosahedron should be deprioritized from consideration for the same. And with that, I'll say that I'm honored to have had the opportunity to speak here at the IAC, and I look forward to meeting with you all and sharing ideas over the course of the week. Thank you.
Thank you, Elliott. Any question?
Yeah, I have one question. So thank you for your presentation. It's really interesting. About the final choice, so the number 1 in the rank, could you elaborate more on possible, let's say, advantages or limitations in long-term perspective for future space applications with respect to more traditional shapes?
Right. So I think everybody is, aware the traditional form for habitat modules is more of a cylindrical form. Now every habitat that is a cylinder will have its own exterior perimeter that needs to be protected from the vacuum of space. If we're able to create agglomerations of space-filling shapes, for instance, you will see improvements in circulation. So it doesn't necessarily have to be linear branches off of each other, which can be create disadvantages that I alluded to in the looping pathways metric. For example, dead-end corridors. If there's an emergency in the middle that separates one astronaut from safety, having multiple ways to get around that can be advantageous. If you can surround space with space fill-in modules, you can get added benefit of enclosed volume without sending up additional resources to create that. And as far as interior volume goes, you're not limited to just with like the inflatable habitats or telescoping habitats. You're not limited to the volume of a fairing for sending up large masses that can be or large volumes that can be assembled on orbit. Are some advantages.
Thank you. And another point, I also like the parallel you did in the paper with some natural shapes, like hexagon or others, if you want to also talk about that, because I think it's an interesting point to make also.
Yeah, there's only so many things you can transfer from the paper to the presentation, but in the paper I end with an example that was used by Fresina in one of his papers on using the truncated octahedron. And he talked about the honeycomb using hexagons, and that is a really most famous example in nature of geometry. However, it's not exactly just a hexagonal tube. You'll see if you look at a hexagon or the honeycomb, that the back of the honeycomb is actually offset on either side. And so the shape of the back is actually rhombuses. And actually, if you use a rhombic dodecahedron, you'll see a profile of this. You can actually insert a shape of a rhombic dodecahedron into a honeycomb cell, and it will fit the shape of the honeycomb cell. And we were actually in the exhibition hall earlier, and you can see this for yourself if you go to one of the exhibits that has offset hexagonal grids in a display case. If you look in from above, you'll see the rhombus shapes of the offset hexagon grids.
Thank you.
Thank you.
Thank you again, Elliott. Okay, thank you.